Hi, and welcome to the Assembly Lines podcast. I'm Chris Torrance. For the past few weeks, we've been working on my Apple II emulator in the browser, written in React and TypeScript. One thing that's been a struggle is how to get programs into the emulator. I wrote a simple assembler so we could get some simple machine code programs in, and I also got copy and paste working so we can paste basic programs in at the prompt. But what we'd really like to do is be able to import floppy disk images. Today, I want to see if I can add support for that. So let's get started. In the last episode, I managed to get graphics working in my emulator. So this is both low resolution and high resolution graphics. And to test it out, I was just pasting in simple AppleSoft basic programs. Let's just show how that works again. So here's my Apple II emulator running in Chrome. And this is written using React and TypeScript. So I've got it booting right now. I can hit reset. And then I can just paste in a program and then just run it. And you can see this just draws the low-res graphics to the screen. And then high-res graphics also work as well. However, of course, the problem is, there's a limit to how big of a basic program you can really paste in before it just takes forever. And if you want to do anything really complex, you want to use an assembly language program. And what you really want to do is load it from a disk image. So that's the next thing that I wanted to tackle. I originally thought that doing the low-res and high-res graphics was going to be the major challenge. However, that was before I turned my attention to floppy disk image support. To get started, I used a couple different reference books. The first one is the Beneath Apple DOS and Beneath Apple Pro DOS series of books. These are both excellent introductions. They have sample machine language programs that you can try, and they also detail the inner workings of DOS. However, to get to the next level, you really have to look at what the Disk2 controller card and the analog card within the Disk2 drive are actually doing. And for that, the one reference that you'll truly need is Understanding the Apple II by Jim Sather. And this is indispensable if you want to truly understand what the Disk2 is doing. Now, I won't pretend that I'm an expert in floppy disks and how they're actually written using the Apple II. However, I'll try to give my best high-level 10,000-foot view of how it works and how we're going to try and implement it within my emulator. So let's dive right in. The first thing we need to do is find a way to import disk images into the emulator, and I decided I would just add a button with a picture of the floppy drive. So let's go ahead and do that. I created a disk drive class, and in that I'm just returning a button. So if we go over to my disk drive class here, and we'll go down to the render method. So I have a button with a picture of a disk 2, and then I've actually wired it up so it'll show the appropriate lights when the motor's running or not, and then whether there's actually a disk in it or not. So if we go over to my display.tsx, we can just enable this, and you can see right here I've just commented it out. And now, if I save this, and you can see I now have a nice, cute Disk 2 button down here on the bottom. If I click on this, I can actually pick a image. So let's say, for example, this games.waz, and it actually shows that the drive door is now closed. Now, it doesn't actually do anything. If I click boot, you can see the light comes on, which is fine. That's just because it knows there's a disk image in there. And you can also hear that I have the disk noises working. So here's the disk motor. And I just recorded these noises off of my own floppy drive that I had since I was a kid. So you might be asking yourself, how did it know whether to draw the image of the disk on or off or open or closed? I have 4 different disk images, and you can see those right here. So here's off, empty, off with a disk in it, on but empty, and then on with a disk in it. And if we go look at my code over here in the render method for disk drive, I have a function called play motor noise, which we'll get to in a second. And then I just choose which image to display in that button. So if my motor's still on and I have disk data, then I'm going to show my disk 2 on. If my motor's already timed out, then I'm going to show that I have a disk in there, but the motor's off. And then similarly, if there is no disk in the drive, then I have the 2 versions for empty. And then when I actually display my image, I just choose the appropriate image variable. Let's take a look now at play motor noise, and that'll lead us to some other interesting things like the soft switches inside the Apple II. So for the play motor noise function, all I'm doing is I'm seeing, is my drive motor set? And so what is this switches.drive.set? Let's take a look at that now. This is over in our motherboard.ts file, and I have an array of all of the soft switches that I've needed to add so far to my emulator. So you can see I have a function here called new switch, and this just takes the address off of that soft switch within the Apple II, and then optionally you can add the address on as well as a Boolean indicating should it be set to begin with or not. For most of these, you can see that all I needed to do was just specify the address off, and it'll automatically fill in the address on as just the address off plus 1. And the default is to have those soft switches be off. The only one that needed to be on to begin with is the text page 1. So you can see here I have text page 1. I have mixed graphics and text. Here is page 2 of either graphics or text. And then finally whether we're in high res mode or not. Now the new ones that I had to add are all of these drive ones. And so these start at address C080, but then offset by whatever slot you've decided your emulator disk 2 is in. In this case, I'm choosing to put it into slot 6. And so you can see that it actually offsets all of those soft switches by 0x60. So there's 8 soft switches that control the disk 2 on an Apple II, and these are 4 phase motor switches, and we'll get to these in a little bit when we talk about how the disk 2 actually works. We have a drive on or off switch, so this turns on or off the motor. We have which drive is actually being turned on. Is it drive 1 or drive 2? And then finally we have 2 more which are a little bit complicated, but these basically determine whether you're in read or write mode for the disk. This last one is probably the most complicated, and this is whether you're shifting the data register within the floppy drive controller or whether you're loading new data. And this works by interacting with both the read-write as well as other switches. And we'll talk more about that in a little bit. So now let's go back to the disk drive code and look at how we're using these soft switches. So now in my play motor noise, this should hopefully make a little bit more sense. It's just saying if the drive motor is currently not set, then go ahead and return. Otherwise, we're going to play our sound effect for the motor noise. To actually play the motor noise, I'm just using simple MP3 files that I recorded off of my floppy drive. And I'm just loading these up into an audio context using some HTML5 features for audio, setting the volume, and then just starting them, and then pausing them when the motor turns off. You can see here that I've tried to emulate the Apple II's method of keeping the motor on for an additional 1 second by just setting a timeout here. So even after I've received the motor off soft switch, the motor noise itself will go on for another second. Now, this is a little bit artificial in an emulator since there's no real motor spinning, but it gives a nice effect and it seems more realistic. All right, so now we've got it so it starts the motor up on boot, spins it, and then when you hit reset, it turns it off. but we're not actually doing anything with this disk image. So we need to figure out a way to get actual bits off of our floppy disk image and into our Apple II. And this is where we're going to have to dive into how the data is actually encoded within the disk image, and then how the Apple II actually reads data off of a real floppy disk. To understand how we're going to get floppy disk images into our emulator, we also have to understand the physical hardware that's involved and where our emulator actually enters the equation for that. On the Apple II, there's really 4 pieces of hardware that are involved. First, there's the floppy disk itself. This goes into the floppy drive. The Apple II disk drive has a small controller board within it that handles reading the magnetic fluxes off of the floppy drive and then delivering those to the Disk 2 interface card that's within the computer itself, typically in slot 6. From there, these signals go into the main ROM of the Apple II and RAM itself, where you have the disk operating system. The interesting thing about the way Steve Wozniak designed the floppy drive controller for the Apple II is most of it is software controlled. So for the Apple II, you have a lot more control over how the data is read and written. This is both good and bad. It leads to a lot of complexity for the software developer who's trying to write their own disk operating system, but it also allows you a lot of flexibility in how you read and write disks. And this also explains why there were so many different types of copy protection on Apple II disks, is because they had the freedom and the luxury of being able to control all of the bits and how they were written to disk. For our emulator, we need to figure out where we fit into this equation. If we were creating a physical device such as the W drive that plugs into a Disk 2 controller card, then we would essentially be emulating the Disk 2 drive itself. And so we would have to handle things like translating floppy disk images into ones and zeros that the Disk 2 controller could understand. Instead, for an emulator such as ours or something like Virtual 2 or AppleWin, we're actually emulating not just the disk drive itself, but also the Disk 2 interface card that goes into a virtual slot on the computer. And so the output that we deliver is slightly different, and it's important to understand the distinction between these 2 different types of emulators, either a hardware one that's plugging into a controller card or a software one like ours that's emulating the entire card itself. Regardless, let's take a look now at the structure of a floppy disk and how that relates to a disk image. For a typical Apple II floppy disk, there are 35 tracks arranged in concentric circles, with track 0 on the outside and going into track 34 as the innermost track. Each track on the disk is typically subdivided into 16 sectors. It used to be 13 sectors when the Apple II disk drive originally came out, but by changing the encoding, they were able to up this to 16 sectors and pack more data in. Now, each sector can hold 256 bytes. So if you do the math, with 256 bytes per sector, 16 sectors times 35 tracks, this gives you a total of 140K of data per floppy disk. Unfortunately, things are a little bit more complex because of limitations of the Apple disk drive hardware. For example, you can't actually store 256 bytes of raw data per sector. Instead, you have to actually encode or nibblize the data due to the way that the disk drive actually stores the ones and zeros. In fact, there really is no true 0 bit on a floppy disk. Instead, you have ones followed by gaps. And the way that the hardware actually works is, as the gaps occur, the floppy drive assumes that those are zeros. If the gap gets long enough, it will keep outputting zeros, but then it starts assuming that there must be something maybe wrong with the magnetic data on the disk, and it just starts increasing the gain until eventually it just starts outputting random ones and zeros. So there's limitations on the type of bytes that you can actually store. And in particular, the limitations are that you have to have the high bit set on every byte of data. You can have no more than 2 consecutive 0 bits set, and each byte can have at most 1 pair of these 0 bits. When you do the math, it turns out that there are only 64 possible values that you can reliably store on a floppy disk. And so this leads to the well-known 6+2 encoding that Wozniak came up with for storing data on a floppy disk. And then when you do the math on that, that turns out that your 256 bytes actually requires 342 bytes to store that same data. Now things get a little bit more interesting because the Apple floppy disk also doesn't use any sort of hard sectoring to locate the beginnings of sectors on a track. If you look at a typical floppy disk, there's a small hole just off to the side of the main hole, and then within that, the floppy disk itself has at least one hole and sometimes multiple holes. These were used for hard sectoring, where the disk drive could actually use that hole to sync up the beginning of a track. However, the Apple II disk drive completely ignores those holes and uses instead what's called soft sectoring. To locate the beginning of a track then and the beginning of a sector, the Apple II instead uses auto-sync or self-syncing bytes, which are actually 10-bit bytes consisting of an FF or a 255 followed by 2 0 bits. And so this adds even more complexity because these have to be encoded and decoded as you're reading the data off the disk. When I was looking into supporting floppy disk images for my emulator, there are a bunch of different formats that are available. The primary ones are DSK disk images or the newer WAS format, which John Kenny Morris came out with to support his applesauce hardware product. If you look at the internal structure of these two file formats, a DSK image is really just the final bytes themselves after all of the encoding has been removed. So it's just 256 bytes per sector times the 16 sectors times 35 tracks. So this is the most succinct form of encoding the data as just the final bytes. If you look at the WAS file format, by contrast, this is actually closer to the raw data that's actually on the floppy disk. So it's really the ones and zeros. So this includes all of the nibblizing and encoding that happens. So for example, each sector actually has the 342 encoded bytes as well as the header information, including the address fields and the 10-bit FFs that are used for self-syncing. So it turns out that if you're actually writing an emulator, the WAS file format is actually more convenient. The Apple II DOS is expecting to get all of those self-sync bytes as well as the nibblized bytes and then convert them back into the final data bytes. And so if you're trying to do this with a DSK image, you're going to have to do the conversion in one direction to fool it into thinking it's dealing with a floppy disk. Whereas with the WAS file format, you can just feed it a stream of bits and DOS will just take care of handling all the nibblizing or denibblizing for you. Let's take a look now at my program and see how we handle all of this. All right, if you recall from a few minutes ago, I had this handle drive soft switches function over in my new disk drive file. And this is just going to take all of these soft switches that are up in the appropriate slot 6 address range and then take action depending on what those are. The first thing we need to worry about is handling the movement of the virtual drive arm. So remember that I said that the Apple II is really completely in charge of controlling the disk drive. The Apple II disk drive has 4 phase or stepper motors that control the position of the drive arm as it moves inward and outward to each individual track. And this is controlled by 4 phase switches. These stepper motors need to be turned on and off in a particular sequence in order to move the arm. If these stepper motors are turned off in an ascending order, say 0, 1, 2, 3, and back to 0 again, then the drive arm will move inward to a higher track number. Whereas if the motors are turned on in a descending order, so 3, 2, 1, 0, back around to 3 again, then the drive arm will move outward or descending. And so you can see here in my code, all I'm doing is I'm checking the order of the phase switches, and then I just call this move head function that I've written to move the virtual drive arm either outward or inward. And if we go up to this move head, you can see here that I have a global track number, and this just gets either incremented or decremented depending on the offset that gets passed in. Now, one of the consequences of Steve Wozniak stripping out a lot of the chips and hence the smarts out of the Disk2 floppy drive is it really has no idea when you first start up which track it's on. Now, the way that DOS handled this is when you first turn the computer on, it would just order the disk drive to descend something like 50 tracks, and then it would know that it was at track 0. And this is the familiar chunking noise that you hear when you turn a computer on. That's just the drive arm itself slamming into the end of its travel, and then you know that you're on track 0. And so I've simulated this by, if the track is out of range, then I have an MP3 that contains a recording of my disk drive just making that noise. Otherwise, it goes ahead and it just offsets the track and then plays a different sound if it's just going from one track to the next. So let's take a look and see what that sounds like. I'll go over to my emulator and I'll just boot it with no drive in there. Okay, so you can see that it started up and then it immediately made that noise, and that's just the drive arm virtually hitting the end of the track and going beyond track 0. So at that point we know we're at track 0. Now let's go back and we'll continue with our look at the handled drive soft switches. For reading data off of a floppy disk, there are two soft switches that you need to worry about. One is whether you're in read or write mode, and the other one is the actual shifting and loading the data register soft switch. So the read-write one is at C08E and C08F plus your slot number. The shift and load data register is at C08C and C08D, again, plus the slot number, which in our case would be slot 6 or 60 hex. So what we do here is in my handled drive switches, we need to make sure that we're in read mode. So if the soft switch comes in to turn off writing mode, then we just set this read mode true flag. And then we need to see, okay, has the code passed in the drive data? And this is the C08C address. And if so, then we're going to call our getNextByte function to actually get a byte of data. Before we take a look at the getNextByte function, let's take a look at a WAS file itself and see how it's structured. And this will help us understand how our getNextByte function works. I have a typical WAS file called games.was, and I've opened this up in both a hex editor as well as the applesauce disk editor. And both of them will be valuable to look at the data itself. If we take a look at this games.was file in the hex editor, you can see that it has a 4-byte prologue here indicating that this is a WAS version 2 file, followed by a couple hundred bytes of metadata about the file itself, including things like whether it's a write-protected disk, when it was encoded, and then finally the location of the actual individual tracks within the file, as well as the length of each track in bits. If we scroll down now to the first sector within the first track, that starts right here, and you can see this is the actual data itself. And so here, this FF, this is one of these 10-bit auto-sync or self-sync bytes. There's a bunch of those. You can see here is the familiar D5AA96, which indicates the beginning of an address field. The address field on a sector contains things like the track number and the sector number, and this just lets DOS know where it is on the disk. If we look at this same data over in the applesauce editor, you can see that instead of showing just the raw bits, it's actually understanding that this is an FF, it's a 10-bit FF, here's all these FFs, and then you have a D5AA96 followed by the actual address data, then some more autosync bytes. Then here's another D5AAAD. This is indicating the start of the address block. And then finally, here's 342 bytes of raw data that's been nibblized. And then finally, we start the next sector. One thing to keep in mind if you're trying to write your own emulator and read in disk images is you have to read these disk images at the bit level, not at the byte level. And this bit me, pun intended, when I was trying to actually read in WAS images, because I was trying to just read the raw data as bytes and pass them on to the Apple II, and it just wasn't working. And we can see why if we look at the data in these two different views. So for example, if we look in Applesauce, which understands these 10-bit autosync bytes, you can see here is the D5AA96. And if we go over to the raw hex editor, you can see we got lucky, and here is the D5AA96. However, let's go ahead and look now at the data field coming up. So again, here's a D5AAAD, but that's preceded by 7 of these autosync FFs. So these are 10 bits each. So that's an extra 2 times 7 or 14 bits of zeros that are going to be floating around and are going to shift the bytes so that they don't quite line up properly. So if we look at our raw hex data now, that actually is down here. So that D5AAAD that we saw here is actually jumbled up right here with this F356AAB6. So it's encoded in there, but you actually have to look at the bits themselves to tease it apart. The easiest way to do this and not have to worry about these autosync bits is to just handle the data in 8-bit chunks, but skip any zeros, because we know that for the floppy disk format, a good or a real byte will begin with a high bit set. So what we do is we just loop over the bits, skipping any 0 bits until we get a high bit. And then from there, we just set that high bit, collect the next 7 bits to build up a byte, and then just return that. So this will handle any of those 9-bit or 10-bit self-syncing bytes, and then also properly return the real data bytes. If we look at get next bit, this is where we're actually going and taking a look at the file itself. So when I read in a WAS file format, I'm using the header information to find out the location of each track. I'm stashing that off, and then I'm just looping through all 50,000 bits within each track and just keeping track of where I am, and then just returning the individual bits as I go along through that track. It sounds complicated, but once you can wrap your head around how the data is stored within these floppy disk images and how the Apple II is actually calling out to these soft switches to read the data, then everything just kind of works like magic. So let's see that in action. If I go back to my emulator now and I click on the disk image, I can actually pick, say, my games disk and then just hit boot on that. So you can see it going down to track 0. This is the track number, by the way, here. It's now reading in the data, and it's actually booted up the disk and displayed the hello program. Now, my code doesn't handle writing to disk, so I can't run anything that's actually going to do something like save high scores or need to stash off anything onto the disk. But we can now run actual simple programs. So for example, let me just hit 2 here to bring up Snoggle. And this is also going to show off my new improved sound for the Apple II, which I managed to work out how to do. Okay, so you can see that I now have my emulator reading disk images, and I still need to work on writing because it doesn't do anything like that. There's a couple things I should point out about the way I implemented reading disk data that aren't quite right, but I'm hoping that for what I'm doing with my emulator, it'll be okay. In my code, when it calls getNextByte, it goes ahead and bundles up all 8 bits and returns them immediately as a full byte. In real Apple II hardware, it starts returning bits as soon as it gets them, and it just shifts those bits over as more and more come in. So if you look at DOS code, it'll typically have a tight loop where it's just waiting for the high bit to be set before it knows that it's gotten a true full byte. In my code, it's going to immediately return a full byte with the high bit set, and so that loop isn't going to execute more than once. I think this is okay for most cases. In fact, it'll actually speed up disk reading a little bit because it won't have to do those tight loops. It'll just immediately be done getting the byte. However, I can imagine cases where if you had critical timing that was depending on those bits being read slowly enough, then that might mess things up. I'm also taking a few liberties with where I'm starting on the tracks. And if you look on John Kenny Morris's Applesauce website, he talks about writing emulators and how you have to be careful for where you jump into the track data, especially with copy protected disks. So I don't think anything like that would work on my emulator, at least not right now, or not with more effort. But I think we've done enough for now. We can actually read floppy disks, and so next time we'll take a look at how to actually write out to disk. All right, I think we made a lot of progress today. We managed to get import of floppy disk images to work. So we can now import both WAS1 and WAS2 files. We can only do reading right now. Writing doesn't work, so that'll be something we'll have to tackle in the future. Also, if you'll notice, I made some slight improvements to the sound, and I'll go over in the next episode how I did that, and finally also show how I added support for joysticks. As always, if you haven't subscribed to my channel, I'd really appreciate it if you'd hit the subscribe button. Also, I have a Patreon if you'd like to support me that way and get your name in the credits. You'll find a link for that in the show notes below. Until next time, thanks for watching.